Yeah, I know that she's almost as cute. She's almost as cute now. So, all right, let's see if I can get this switch. There we go. Cnfrmers some more today. So we ended talking about all the cyclopropane versus cyclobutane, and how we had to get to where the Vesper geometries were reasonably close to what they were supposed to be. And we had those things too close to each other. So when you have things attached to the same carbon. So if you think of this bromine, the front carbon and the back carbon, a flat surface, the dihedral is how far out of that flat surface is the bromine. So if we picture, here's a nice flat plane right here, right? So we have one of the top bromine right here, and then the second bromine, 4, 5, 6, 7. So it's heptane, and it doesn't matter which way we count, it's heptane, right? And if we count down, here, 1, 2, 3, 4, 5, 6, 7, it matches up with counting over here, 1, 2, 3, 4, 5, 6, 7. You wind up, let's see, so I'm not very good at, you have to turn on and editing in order to be able to draw on the slides here. If we call this carbon 1 for the left-hand example and this carbon 1 for the right-hand example, you can count like this versus straight from right to left here. We see that we have two methyls that are on carbons 2 and 4 and an ethyl on carbon 3 in both cases. It's a little bit trickier to picture. But the other thing you can do is, so this is actually one case where a complicated branch can actually be helpful. Bromines should be on the left-hand side. Both of our chlorines should be the right-hand side, and then a methyl up and a methyl down. And the methyl up is on the eclipsed carbon, so I have this drawn backwards. So it shows the importance of making sure you get it set up right to begin with. Our front carbon looks like a Y, right? Because we have something in the plane sticking straight down, and then something up and to the left and up and to the right. So our front carbon looks like this, and it's going to, for a lot of plastics, winds up being more significant. And as we get more and more, there's always been, there's a push since really since the 60s for chemistry in general to be more green, especially educationally, because the more we can use green products in the teaching labs for chemistry, the more demand there will be for using safer and cleaner processes and things like that, and general waste. So there's actually an entire field of chemistry called green chemistry dedicated to where can chemists be better when it comes to solvents we're picking, the labs we're choosing, what we're doing with our waste and things like that. You can rotate, right? Again, mold view is really helpful for that. Same shape. See if I can get oriented the same way as it is. So what we're looking at with that Newman projection is basically taking these two carbons and looking down that bond, and you see that they're just barely, right? So I'm still fairly staggered, fairly eclipsed, but actually everything on mold view is actually more helpful than just looking at this, because this is still kind of an abstract idea. It takes some getting used to, or get some models and build cyclopentane. And you'll be able to actually hold it in your hand and twist it around and see it. And you'll see that when you make this coverage shape, and it will naturally make a puckered shape. And in that case, we would see a difference in the heat of combustion because we're in the less sterically favored state. We're forcing the other both conformer, both of these two carbons have hydrogens still sticking off of them, right? Which wind up running into the hydrogens on the other side. I'm not sure why they call them flagpole interactions, other than, you know, if you picture both ends of a boat, if you have a flag at the front of the boat, a flag at the back of the boat, they might be sort of pointed a little bit towards each other. You can visualize that these things would be trying to occupy some of the same space as well. So one more idea, and then we'll take our break, is that because of these interactions, because of the eclipsed state and the flagpole interactions, these flagpole interactions are happening because these hydrogens want to be in the same place, right? They're kind of lined up head to head like this. Well, you could minimize that if you just took those 2 points and sort of twisted them a little bit. Right, so they actually, the stable form, the stable conformer of the both conformer is not symmetric the way it's drawn here. Because if you take these 2 points and move one of them back and one of them forward a little bit, but then all of a sudden these hydrogens are pointed slightly offset from each other. So they actually call that the twist boat of the between chair and twist boat. So it's halfway up here, and then as it gets all the way up and things settle sideways a little bit, you get twist boat. If you make that boat be symmetric, you are going to get to another transition state where you're forcing it to be unstable. You're forcing those flagpole interactions. You're basically going from twist boat. If you force them to be flat, that's another transition state, because then they're going to do that. They're going to continue that rotation. So you get one twist boat versus the other twist boat is basically going from here to here. And then you could go the other way. You could flip down the other side to get to the chair conformer once again. All right, so I know that this is a complicated potential energy surface. We'll break it down and spend more time with it in about 10 minutes. Let's say come back at 1/4 and I'll have some models.
It's supposed to be a good bang for your buck, but it doesn't have the same feel. It's small.
Yeah, Subarus did this. They got to it. I think they were actually going for a bow tie, but it looks like a cyclohexane once you're in OChem. So when we have these, and I'm actually going to go through and add my hydrogens to this drawing I just did. I'll just say it's right in the middle here. I'm actually going to blow it up even a little bit more. And a bond going, it's flat. And I'm going to draw it a little thicker to indicate, just like with this one here, that it's in the plane and in front of. That's a lot better than this one. This one doesn't look that good. Let's fix that one. Right, so that Vesper geometry says they should go. And you can show them with wedges on the front and back if you want to. It can be helpful to do that when you're getting used to what these actually look like in dimensions. And it should look like your model. So why do we care about labeling these versus equatorial? Well, because these axial ones all point the same way, like we were talking about, right?